Alright, welcome back everybody with momentum. Today we are primarily talking about impulse, but what is impulse? So impulse is the change in momentum. If an object increases or decreases its velocity, that means an impulse has been imparted onto it. So impulse is equal to change in momentum. Okay, whenever we see this triangle shape, that means change. And we should already know this lowercase p is momentum. So change is always final minus initial. So final momentum at mass times velocity final squared. Mass times velocity final minus mass times velocity initial. Okay, so there's two formulas for it. That's one formula. And then the impulse is also force times time. So in order for something to change momentum, there needs to be a force acting on it for a certain amount of time. Okay? So these are the two formulas that we're going to use. And we see it over here with its algebraic manipulations. So if you want to copy it down, write it down, memorize it, or anything, you can do so here. Alright, moving on. So a rocket ship is cruising through space with its engine off, traveling with a constant velocity of 400 meters per second. What force is imparting impulse, changing the momentum on the rocket? A, friction, B, tension, C, thrust, D, impulse is not being imparted onto the rocket ship. Make sure to pause before I give the answer. So, a few things here. The answer is D. Impulse is not being imparted onto the rocket ship. Well, how do we know? Well, one thing is it's not changing its motion. It has a constant velocity of 400 meters per second. There is no force acting on it. In space, there is no air resistance. There's no air. There is no friction or anything like that. For the most part. So it's just cruising through space. No force is acting on it. So no impulse is acting on it. Alright, next question. A rock is, example number 6. A rock is initially at rest and then starts to move by a person pushing on it. What force is imparting impulse, changing the momentum on the rock? Force applied, force tension, normal force, impulse is not being imparted onto the rock. The answer is force applied. So there is no tension. There is a normal force over here, but the normal force is not changing its momentum. What's changing its momentum is the force applied. So that's why impulse is imparted by the force applied. A ball is rolling down a hill and the ball is getting faster and faster. What force is imparting impulse, changing the momentum on the ball? A, force applied, B, force of gravity, C, normal force, D, impulse is not being imparted onto the ball. The answer is force of gravity. Gravity is making it go faster and faster as it goes down the hill, changing its momentum to be more and more. Conceptual example 8. A glass cup slides to the right and slows to a stop. What force is imparting impulse, changing the momentum on the ball? A, force of friction, B, force of gravity, C, normal force, D, no impulse. The answer is going to be force of friction. So even though there is gravity acting on this and there is normal force acting on this, that's not what's changing its velocity or changing its momentum. Okay, what's changing its momentum and making it less and less is the force of friction as it is sliding. Okay, so force of friction is imparting impulse. Alright, number 9. A ball is pitched moving with a constant velocity until it's hit with a bat. What force imparting impulse, changing the momentum on the ball? A, normal force, B, force of tension, C, force by the bat, D, impulse is not being imparted. So anyway, you should probably get the point by now. It's going to be the force by the bat. Okay, moving on. A box of 10 kilograms is initially at rest on a frictionless surface. It is then pushed with a force of 20 newtons for 3 seconds. What is the impulse imparted onto the box? Okay. So we should know that impulse is equal to force times time. So the force, this guy is pushing, this guy's going to be pushing on it with 20 newtons. 20 newtons for a time of 3 seconds. So the impulse is going to be 60 newtons squared. Not newtons squared, newtons second. Okay. B is how fast is the box moving after being pushed for 3 seconds. So you can do this with what we learned with Newton's laws. And actually Newton thought about Newton's third law more with this kind of formula. But we should also know that impulse is equal to change in momentum. We know impulse is equal to 60, and we know change in momentum is mass times velocity final minus mass times velocity initial. So we know 60 is equal to mass, which is 10, velocity final, which is what we're looking for, minus mass, which is 10, times velocity initial, which is 0. It's initially at rest. So let's simplify this. 60 is equal to 10 VF, and this is just 0. So we could divide both sides by 10, and we get velocity final is equal to 6 meters per second. Okay, so after this guy pushes on it for 20 newtons for 3 seconds, it's now going 6 meters per second. Okay, change this momentum. Oops. All right, conceptual example number 10. Scenario number 1. A box of 10 kilograms is initially at rest on a frictionless surface. It is then pushed with a force of 20 newtons for 3 seconds. Okay. Scenario number 2. A box of 40 kilograms is initially at rest on a frictionless surface. It is then pushed with a force of 20 newtons for 3 seconds. Which scenario will the box be imparted with more impulse? Scenario number 1 or scenario number 2? Now think about it. This one is a little bit more confusing. One thing we know is scenario number 2, the box is a lot bigger, has a lot more mass. But another thing we should also notice is they are pushed for the same amount of time with the same amount of force. Being parted with more impulse, the answer is C, both are the same. How do we know that? Impulse is equal to force times time. So they both have 20 newtons of force acting on the box and for 3 seconds. So in this case, they're actually both going to have 60 newtons second. Okay. And that might seem weird. You might be like, well, the scenario number 1, it's going to be going faster. So shouldn't the change of momentum be more? Or you might be like, oh, scenario number 2, the box is bigger. So shouldn't the change of momentum be more? Well, yeah, it's bigger, but it's going to be going slower. This is smaller, but it's going to be going faster. So it turns out to be the same. Change in momentum. All right, conceptual example number 11. Similar question. A box of 10 kilograms is initially at rest on a frictionless surface. It is then pushed with a force of 20 newtons for 3 seconds. A box of 40 kilograms is initially at rest on a frictionless surface. It is then pushed with a force of 20 newtons for 3 seconds. Which scenario will the box be moving faster? So from the last example, we realized that the impulse is the same, and that's 60. However, even though the impulse is the same, and that also means the change in momentum is the same, that doesn't mean that the velocity is going to be the same. So since this box is a lot smaller, it will get a lot faster quicker. So the answer is scenario number 1. And the reason for that, and you can do it mathematically, but the reason for that is because the mass is a lot less. Okay, moving on. A 0.7 kilogram ball is pitched at 40 meters per second to the right. A baseball player hits the ball, and the ball moves to the left at 60 meters per second. What is the magnitude of the impulse imparted onto the ball? So this one's going to be a little bit confusing. Maybe I'll draw it here. This ball is moving to the right initially at 40 meters per second. Okay, it gets hit by the ball. And now I'm going to draw this dotted. It is now moving 60 meters per second to the left after it's hit. Okay, so we should know that impulse is equal to change in momentum. So this means the final momentum minus the initial momentum. So let's kind of write this out. So final is after it got hit. So after it got hit, it's going to the left 60 meters per second. So the ball is 0.7, but it's going to the left, so I'm going to put negative 60 here. And then I'm going to do minus mass, which is 0.7. And before it was hit, it was going 40 meters per second to the right, so that's positive. So I'm going to write this out, or I'm going to put it into my calculator. 0.7 times negative 60 minus, 0.7 times negative 60 minus 0.7 times 40. And I get negative 70 Newton second. However, it does ask for the magnitude, so it just wants the positive answer, 70 Newton second. Part B, if the batter hit the ball with a force of 720 newtons of force, how long was the ball in contact with the ball? How long was the bat in contact with the ball? Okay, so again, we know that the impulse is 70 newton per second. Oh, sorry, I should write this. We should know that impulse is also equal to force times time. And in this scenario, we know the impulse is 70. The force is 720. And we're looking for the time of contact. Okay, in contact. So I'm going to do 70 divided by 720. And I get a time of 0.097 seconds. Okay. Alright, that was a little bit difficult, so watch it again if it didn't make sense. Alright, next example here. A little tricky, so think about this before seeing the answer. Car number 1, call this one over here, crashed into a highway barrier filled with water. Oops, that's not number 1. This is the one filled with water. Okay. Car number 2 crashes into a concrete barrier. Both barriers exert the same amount of impulse to stop the cars. However, the water-filled highway barrier takes a lot longer to make the car stop than the concrete barrier. Which car will experience more force during the crash? Okay. So, 2 things to know about these kind of problems. It is confusing. Impulse is first equal to the change in momentum. So, we know that they both start with the same speed. And then when they hit their barriers, they're going to come to a stop. So that means that the impulse and the change in momentum in both scenarios are the same. However, even though their impulse might be the same, that doesn't mean that the force they experience in the crash is going to be the same. We should also know that impulse is equal to force times time. So we should know for scenario number 1 and scenario number 2, the impulse is the same for both. They both start with the same amount of mass and speed, but then they all both end up with 0 momentum because they come to a stop. However, we should know with car number 1 or scenario number 1, when it hits this barrier, it's going to take more time for it to come to a stop because the water barrier isn't as, hard. So it will come to a stop. It'll take more time to come to a stop. However, the concrete barrier is very hard, so it'll come to a stop immediately, so it'll be very short time before it comes to a stop. So, one thing to know is, if this time takes a lot longer for it to stop, then that means this force is going to be a lot less. Okay, so because the impulse has to be the same in both scenarios, the longer something takes, the less force it's going to be. The shorter amount of force that something is, the more force there's going to be. So in that case, it's going to be car number 2. Which car will experience more force? Yeah, because it's going to come to a stop in a very short amount of time, which means a large amount of force is going to make it stop in that short amount of time. While in this one, it's going to take a long amount of time for it to stop, so that means a smaller force is going to be acting on it for that long period of time. I hope that makes sense. Watch it again if it doesn't. It is a little tricky. Okay, pretty cool video to learn a little bit more about impulse, so watch that. Alright, number 13. A car is moving at 40 meters per second, then slams into a wall, coming to a quick stop. In one scenario where the person crashes, there are airbags, and in the second scenario, there are no airbags. In which scenario will there be more impulse? Usually, your impulse or your initial thinking is going to be like, oh, okay, the one with airbags is going to be less force, so the one with more force is going to have more impulse. So, it could be like decent thinking, but it's not exactly correct. It is true that the one with the airbag is going to have less force, but we should also know impulse is equal to change in momentum. So what we know is when it comes to a crash, it's and we know change in momentum, mv final minus mv initial. When it comes to a crash, the final velocity is going to be 0. So that means the initial velocity is going to be the same for both scenarios, and the mass is going to be the same. So whether it comes to a crash and the person stops immediately or takes more time to stop, the change in momentum is going to be the same. So both will experience the same amount of momentum. Just Just an FYI. Okay, this video will kind of help with the next one, kind of showing how airbags work. So next question. A car is moving at 40 meters per second, then slams into a wall, coming to a quick stop. In one scenario where the person crashes, there are airbags, and in the second scenario, there are no airbags. In which scenario will there be more force on the driver? Okay, so when you crash and there's no airbag, this person here is going to immediately hit the steering wheel, hit the car, and very quickly, with a very short amount of time, going to stop. Remember, impulse is the same in both scenarios, but if it's going to be in a short amount of time, that means there's going to be a large amount of force making it come to us a time. But when it has an airbag, what happens is the airbag slows down the impact. It's going to take a longer time for the person to hit the airbag, so there's going to be a larger amount of time, meaning a smaller amount of force. So in one scenario where the person crashes, there are airbags, and in the second scenario, there are no airbags. There will be more force with the no airbags. Oh, second scenario, there are no airbags. Will there be more? Oh, sorry, that should be scenario number 2. Let me change that. There you go. Okay, moving on. A car is moving at 40 meters per second, then slams into a wall, coming to a quick stop. In one scenario where the person crashing, there are airbags, and in the second scenario, there are no airbags. In which scenario will there be a longer duration of the stopping force? So like we already mentioned, when it has airbag, it's going to come in contact with while it's crashing, it's going to be in contact with the airbag a lot longer than if it crashes and it just hits the steering wheel. That would just be an instant, while the airbag is going to take a longer impact. And if you saw the video, you'll see that as well. Okay, so scenario number 1, where there are airbags. All right, example number 7. Charlie is playing t-ball. He swings at 0.144 kilogram ball that is at rest and hits it with a force of 182 newtons, which is in contact with the ball for 0.009 seconds. What is the impulse exerted on the ball? Okay, so we know that impulse is equal to force times time. So force is 182. And the time is 0.009 seconds. So let's see. 182 times 0.009. And we get 1.64 Newton seconds. Part B is how fast will the ball be traveling after it was hit? So we should also know impulse is equal to change in momentum. So now we know the mass of the ball is 0.144 kilograms, and we're looking for the final velocity minus the momentum at the beginning, which is 0.144. But in t-ball, at the very beginning, the ball is not moving, so this is just 0. And we know the impulse is 1.64. So let's see, we can do 1.64 is equal to 0.144 times velocity final. Divide both sides by 0.144. And we get velocity final is equal to 1.64 divided by 0.144. 11.39 meters per second. Okay, great. Moving on. Okay. Interactive example, pretty cool. So if you want to look at it, feel free to do so. Okay. Example number 8. Okay, a little tricky here. A 0.5 kilogram ball is thrown to the right at a speed of 20 meters per second. Okay, so it's going 20 meters per second. The ball bounces back from the wall at moving at 12 meters per second. Okay, so it bounces back. Let's kind of draw it like this. And it's going 12 meters per second. What is the magnitude of the impulse of the ball experienced from the wall? Alright, so remember, impulse is also equal to change in momentum. So the mass is 0.5. The final velocity is going to be when it's after it hits the wall. So that's 12 meters per second. But it's going to the left. So we should remember that's negative 12. And it's going to be minus the initial momentum, which is 0.5. And right before it hits the wall, it's going to the right, 20 meters per second. So this will be, let's see, 0.5 times negative 12 minus 0.5 times 20. And we get negative 16. But it asks for the magnitude. So that should be positive 16 Newton second. All right, part B. If the ball was in contact with the wall for 0.2 seconds, what force did the wall exert onto the ball? Okay. So we know impulse is equal to force times time. The impulse is 16. We're looking for force, and the time is 0.2 seconds. So the force is equal to 16 divided by 0.2, and we get 80 newtons. Okay. Hope that makes sense. Moving on. All right, that's the last one. Next time we're going to be talking about collisions, which a lot of this chapter is about. And we're going to be first starting out with perfectly inelastic collisions. All right, thanks for watching, everyone. I'll see you with the next one. Bye.